Algebra 2, this is 8.1 and 8.2 rolled into one. This is exponential growth and decay, and what we're going to do is graph them. And so we have a growth graph and a decay graph for exponential equation. The exponential equation here is in the middle below the graphs. This is what we're going to do is we're going to call this the child again. So we're going to use a parent-family-child method to do this. But what we need to recognize is that growth is different than a decay. Decay, or growth, starts low, ends up going higher. Decay starts at a higher and goes lower. Things that grow exponentially, the money in your savings account or retirement account, usually. Populations, people, rabbits, animals, rabbits for sure, they populate growth. The more rabbits you have, the more rabbits you get. Boom, more. Decay, half-life, radioactive materials. They talk about half-life. Well, it's because after so much time, half of the amount's there. Then another so much time, there's half of that amount. Buying a car, as soon as you drive it off the lot, it starts losing its value, it starts falling. Essentially, you can't get something from nothing. So that's why it never reaches zero. That's why we have this dotted purple line down here on each of these, is because you can't start with zero and multiply it to get something. Notice that in our equation that we are multiplying here. So therefore, you're multiplying to get things. Also, likely, you can't start with something and end up with nothing. Even if we're talking about half-life or half of something, if I keep cutting something in half, there's always, mathematically, going to be something there. Just like your car's value. Your car's value will drop. Your car's value will never be zero. You can always junk it for something, right? So, therefore, this is exponential growth and decay. That's what the graphs are going to look like. Essentially, those are what their parents are going to look like in a way. There are some things that are common between both of these. Both of them have a y asymptote at y equals 0. Or not say y asymptote, we're just going to say asymptote at y equals 0. As in parents. So maybe what I'll do here, let me change this just slightly. I'm going to move this down. And we'll get rid of this again. So our parent for both of these is y equals b to the x. Y equals b to the x is our parent that we're going to start off our parents with. And the parents only have 3 pieces of information. And I see I'm running out of room here. So the first one is they all have a y asymptote at 0. So up here, they all have it at 0. It's that line that doesn't really exist on the graph. It's what it approaches, and that's what it is. The other one is it has a y-intercept at 0, 1. All parents have a y-intercept at 0, 1. The next one, and I'm going to squeeze it on the bottom, is an extra point. Now I'm going to put it on the bottom because I'm giving myself room over here, because this is the only thing that changes between being growth or decay. So if I am a growth graph, if you notice here, the tail end, or this end over here on the left, is going towards 0. We know what's going to happen. It's going to eventually approach 0, almost touching it. But what we don't know is what happens over here. Is this graph supposed to be going the way it is, or I'll change colors here, or is it supposed to be more gradual? Or was it supposed to shoot up, straight up like this because it's growing a lot faster than we thought? So we don't know what's happening over here. And so I'm going to pick a point, my extra point way down here, to be a value on the positive side, and put in 1. I'm going to stay close to home, because the bigger the value of x I put in, the larger the number I'm going to get. So I'm going to choose a value like 1. Now likewise, over in decay, I know what's going to happen over here on the right. On the right, it's going towards 0. On the left, again, I have the same situation. I don't know where this is going. So I'm going to pick a value like -1. So I'm going to put in y equals 0 for an asymptote, 0, 1 for a y-intercept, and I'm going to choose one of those 2 points as my extra point. From there, I am going to use the parent, family, child, where A, vertical stretch or shrink, H, my left-right movement, and K is my up and down movement, my translations. So everything else is staying the same. So let's do a problem. So y equals 2 times 3 to the x minus 3 plus 1. Now remember, when we do this, we have to start off with the parent, we move to the family, then we go to the child, and we also place on our bridges what's happening in words. So, parent. The parents stay at home, and we take away all the moving parts. And so if I take away all the moving parts, that means I need to cover up the 2, the negative 3, and the 1. So the 2's gone, the 3's gone, and that 1's gone. So it ends up being y equals 3 to the x. This has information. Y equals 0. Always. That's your asymptote. We have a point. 0, 1. Why is 0, 1 work? Because if I put 0 in for x, 3 to the 0 power is 1. And is this a growth or decay? Oh wait, I forgot to talk about that. After a second. How do I know this one is growth and that one is decay? So we know this one is growth because b is greater than 1. We know this one's decay because b is between 0 and 1. Forgot to state that. Sorry. The base number, the number that's being multiplied or has the exponent, like if you make it a 2, well, 2 to the second power, 2 to the third power, 2 to the fourth power is 2 times 2 times 2 times 2, right? The number keeps getting bigger. But what happens if it's a half? Well, half times a half is a fourth. Times that by half, it's an eighth. It gets smaller. And so that's why your graph falls down for decay and grows for growth. Sorry, let's go continue on. So this is a growth graph because 3, which is our base number, is bigger than 1. So I'm going to choose a value on the right side, like 1. I'm going to put 1 in. I'm going to put 1 in for x. 3 to the first power is 3. This information right there, you just apply your A, your H, and your K to, and you're done. So we go to the family, right? The family is bringing back A, which would be what?
2.
So it'd be 2 times 3 to the x. And what does that 2 do to our graph? Vertical stretch of 2. We don't have to say it's reflected because it's positive. And when I do that, I have to just take 2 and multiply it to all of the y's. Well, y equals 0. That's still y equals 0 because 0 times 2 is 0. 0, 1 becomes 0, 2. 1, comma, 3 times 2, which is 6. So remember, we're multiplying all of these y values by 2. We then can move on to the child. Remember, the child graph is the whole entire thing. And this is where we have to say it's translated. Translated 3 to the right. And it's translated 1 up. When I move it to the right, all my x values go up by what? When I move all my points to the right, my x values go up by 3. Now, it's y equals 0. Is there an x component to that? I don't think there's an x component to this y, so we leave it for now. Start at 0, I end at
3,
start at 1,
4,
go to 4. I'm also going to move up 1. If I start at 0, I end at 1. If I start at 2, I'm at, and I start at 6. Graph that, you're done. That's pretty cool. So, we have a y equals what? 1. So y equals 1 is a dotted horizontal line at y equal 1. That's the line it will not cross or touch. I'm going to plot 3, 3. 1, 2, 3. And plot 1, 6. 1, 2, 3, 4, 5, 6. Nope, not 1, 6. I'm going to plot 4, 7, sorry. And 7, I think I need one extra 1. So 4, 7. You notice that the points here are offset just a little bit. So what I'm going to do is I'm going to start here and start following through, go through the point, and I can't cross that line, so I'm going to curve away along it, okay? And there's your graph.